Day 8. Alright, let's go. So, you're still riding a camel across the desert when you spot a sandstorm quickly approaching. When you turn to warn the elf, she disappears before your eyes. To be fair, she had just finished warning you about ghosts a few minutes ago. One of the camel's pouches is labelled maps. Sure enough, it's full of documents, your puzzle input about how to navigate the desert. At last, you're pretty sure that that's where they are. One of the documents contains a list of left-right instructions, and the rest of the document seems to describe some kind of network. Okay. A graph is our first graph problem. It seems like you're meant to use the left-right instructions to navigate the network. Perhaps if you have the camel follow the same instructions, you can escape the haunted wasteland. After examining the map for a bit, two nodes stick out, AAA and ZZZ. You feel like AAA is where you are now, and you have to follow the left-right instruction until you reach Z. The wording is so interesting. You feel like. It's not you are. It's you feel like. Okay. This format defines each node on the network individually. For example, RL, right, left. So we have A that goes to B, C, B goes D, E, C, Z, G, D goes to D and D. Okay, so it is a graph. Yeah. It's a graph. Cool. Starting with AAA, you need to look up the next element based on the left-right instructions. So you start at A, you go right, and then you go left, you go Z. Okay. Yep. Of course, you might not find ZZ straight right away. If you run out of left-right instructions, repeat the whole sequence of instructions as necessary. Right, left really means right, left, right, left, right, left, blah, blah. So on, for example, here is a situation that takes 6 steps to reach Z. Left, left, right. So B, A, right again, and then left again, then right, then right. Okay. Does each node only have, so is this a tree? Is this like kind of a tree? Yeah, it is kind of a tree. So we can do a node with 2 children, and those children can loop back. Okay. Starting at AAA, follow the left-right instructions. How many steps are required to reach Z? Okay, that doesn't seem too bad. Let's have a look at this simple this simple one for now. First of all, let's take var instructions is equal to input 0. Var map equals input 2 dot dot. I think that's inclusive, but just in case it isn't, I still need to remember how these operations work. All right. Oh, the LSP is not working. Interesting. Why? Can I get some LSP, please? There we go. Great, thank you. Zig run source main. SS. Okay, so that goes. So actually, this needs to be 1 dot dot. Yeah, that's right. Cool. So now let's have a const. It's not a tree node. Tree-ish node. Sure. Which is a struct that's going to have left, which is a pointer to tree-ish node. Comma, comma, and it's going to have, yeah, and the right. It's also going to have a label, which is going to be const_weight, also known as string. And then, yeah, great. So then what we're going to do is we're going to go through this. So for map line, we're going to take just to double check, does the puzzle inputs always have 3 characters? Yep, seems like it. So I'm going to take this, this, and this. So 0, 1, 2 var label equals line between 0 dot dot and then non-inclusive 0, 1, 2. So I think 2 or 3 here. 3. And then left 0, 1, 2, 3, 4, 5, 6, 7, 7, 10, 10, 11, 12, and then 12 to 15. S, L, S, 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 new line, label left and right. Let's just see if we've got that right. So, alright. First try correct. Good. Alright, so what we're going to do is we're going to have then var node equals tree-ish node. It's going to have dot label equals label dot left equals left. Oh wait, interesting. We pass them. I think we probably pass them first. Go like this, store them, and then do another run through. Another run through to fill them in. So we can have a map of. Yeah. Okay. Good. I got an idea. Best way to do this. What is that? Allocator equals stand.heap.page allocator. Cool. So then var node map equals standard.auto hash map, which is a map between const_weight, the label, and a pointer to tree-ish nodes. Let's init it with our allocator and then defer node map dot d-init. We don't want that, we don't want that. We do want this. So what we're going to do is we're going to say node map dot put. We have to try that label and the address of node. That's great. The address of node. We do it once. We do it twice. And we have all the nodes. I'm assuming like they all connect to something, right? You can't have a null child. So we have left to right, and what we're going to do is we're going to say var left node equals node map.get. The key is going to be left. Right node. Right, so those are the addresses, right? So we can do left node dot star dot, what is going on? Yeah, okay, fine. Dot star dot, it really doesn't know what it is, but yeah, that's annoying. But dot left equals oh no, we need the label as well. And what we're going to do, file label node equals node map.get label question mark. And what we're going to do is label node.star left equals left node right node. Do you compile and run? You don't compile and run. Yes, because dot left is null. We can have a null pointer, right? That's a good question. Can we have null pointers in Zig? Question mark. Yeah, let's just add a question mark there then. So that it's potentially not. What do you want? What is this? I can't remember how to define these. Missing struct field left. Well, okay. Dot left equals undefined. Dot right equals undefined. What is this? Auto hash map does not allow slices here because the intent is unclear. Consider using string map. Okay. String hash map. Delete find this. Okay. Compiles and runs. Great. That should be all good then. Hopefully. So starting with the instruction left right. For instructions letter if letter equals R else, so if it's right, starting, which is an array of U8, is equal to AA. Current is equal to node map dot get starting question mark. Yeah, and it doesn't know what that is. So we just got the node for that specific thing, and what we're going to do is go right. So we're going to say actually starting is equal to current dot star dot right dot label, something of the sort. Do you compile and run? You don't compile and run. Oh, dot right dot question mark. Yeah, because we had to leave those undefined for a little bit, so great. And the question? We're going to do while starting is not equal to standard.mem.equal UA starting and zzz. While it isn't equal, var part 1 view size 0. Each time we do an instruction, we do part 1 plus or equal 1. We're going to print part 1. No. 2. Oh, that's right for that input, isn't it? I like this one. 3. So I don't think that's right. So it goes once, twice, thrice, then it checks. Okay, each time we go around the loop, we're going to print the starting starting print node oh god, that's a lot of stuff. We start at A, we go left to B, how do we go to Z? How's that possible? Starting is A, a node. New starting. Here. Let's print some stuff here of current.star.write that question mark dot label. Not you. What? So current label is going to be current.star.label. Okay, so I think we did something silly here. Yeah, we probably did something really weird. We did. Node map get starting. Starting is A. So that's really weird. So we do get and we get A. That can't be right. Let's do a print here. Print of any node map. It's just really strange that we're getting those results. So something is wrong with our construction. The map. Okay, that's really hard to look at. What we're going to do is var iter equals node map dot iterator for iter dot next entry s any. So we're going to go entry dot key pointer dot value dot pointer. There we go. Segment fault. Great. Value dot label. So ZZZ goes to 90, 90, 90. What? Let's put you at S. They all go to Z. What am I doing? What? What the hell? What have I? What cursed thing have I just landed into? They all go to Z. Wow, why? Do node map, not put the label. A, B, 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 Z, Z, Z. That is very, very weird, actually. Do I just severely misunderstand this? So we get the key. Yep, I understand. And then we get the value, right, which is a pointer. Value star dot label. Or if I do dot star dot, because they are pointers to pointers there. We have some indirection, but doesn't matter. Still we get that. Oh, how strange. How very strange. Am I just like, maybe I need to allocate it, like it's just redoing it in the same space of memory and then getting overwritten. But that's really interesting. Maybe this stack allocation here is getting freed or something. That's, I don't know. Maybe what I do then is node equals allocator dot alloc, but I actually just want one, so create. I want to create tree-ish node. So then node dot label is equal to label. Node dot left is equal to undefined. Node dot right is equal to undefined. And then we just never free. And then I need to try that. And node is indeed a pointer already. So that was what was happening. That's really interesting. Huh. I didn't know that could happen, but okay. Now we get 6. That's part 1 answer. Alright. Let's do it. Let's just go. All right, that was sick. That was a really fast part 1. Great. The sandstorm is upon you, and you aren't any closer to escaping the wasteland. You had the camel follow the instructions, but you've barely left the starting position. It's going to take significantly more steps to escape. What if the map isn't for people? What if the map is for ghosts? Are ghosts even bound by the laws of space-time? Only one way to find out. Are these ghosts quantum? Right. After examining the maps a bit longer, your attention is drawn to a curious fact. The number of nodes with names ending in A is equal to the number of nodes ending in Z. If you were a ghost, you'd probably just start at every node that ends in A and follow all the paths at the same time until they all simultaneously end up at... Oh my god, what? Okay, let's keep reading. Yeah, okay, so you basically ignore stuff because they both end with A, as follow left-right instructions simultaneously. Navigate. Okay. This is a caching problem, right? So this is a caching problem because you are not just going to compute one step of every single path. You're going to do it once. B. Yes, that does it twice. But there is another one. A, left, 222, B, right, C. The other one is now gone back. And then 22C, left ends in A. So 2, 3. And you repeat the 3, the 2, and the 6. So 2 times 3, 6. So it's lowest common multiple. But we don't need to do the actual lowest common multiple. We can just multiply them all together because that will still give us something. So what we do is we go through every path, starts with A, and we follow the instructions. Then we do that for every path, and and we gather the numbers, and part 2 is them multiplied. Ooh, but it might not quite be. No, it has to be lowest common multiple, right? It has to be the actual lowest common multiple, because otherwise you might have repeated trips. Imagine one takes 4 and one takes 8. 4 times 8 is 32, but actually the lowest common multiple is 8, so you would only take 8 trips. Okay, so it has to be the lowest common multiple. Fine. What we do is let's take this here. And let's leave that for part 1. What we're going to do is we're going to find the number of paths for start labels. Start paths equals standard dot. Let's do an array list of constraight dot init allocator. Defer allocator dot free starting. Actually, no. Let's just do starting path dot the init. Maybe that's why yesterday I was getting a bunch of weird memory stuff. That's a lowercase l. Was that was copying issue, right? Yeah, that was. Okay. So now what we do is we say we don't really. I'm printing a lot of stuff now. Where am I printing stuff? Here. Node map. It's equals node map dot key iterator. If key at 2 is equal to uppercase A, then we're going to try starting paths dot append key. And then another thing we're going to do is up here for starting path length standard dot array list. We can probably go through the index, right? We can just do usize here. Locator, and we can do path length dot dinit. So what we can do is we can say for starting paths path. We're going to basically do the same thing we did from part 1, right? Length, current, just do S. Let's do an S instead. S, delete there, just S. Why is the indentation here being so strange? There we go. Helped it a little bit. Cool. But it doesn't start at A. It starts at path. Yep. And it's going to do this while delete while S2 is not equal to Z, and it is, we come out here and we say path length dot append the length taken, and after we append the length taken, we do the LCM. Please tell me there is one. There is a function. LCM in Zig. No. Am I gonna have to write it? Okay. I guess. Oh, I don't want to. Okay. Algorithm for LCM multiple numbers. Least common multiple. Yep. Yep. What's the most efficient way to calculate least? Not two integers. With multiple, with n numbers, of n numbers encoding. So LCM is 1 for on an n. The greatest common divisor, so HCF. The general relation is that lowest common multiple of A, B, C is lowest common multiple between the lowest common multiple of A, B, and C. Yeah, that's true, I guess. So we can probably just continue. Yeah, let's do that bottom approach. LCM between two numbers. Simba, stop it. Dog is being loud. Algorithm. Just give me. There you go. Still like doesn't, you know. Still doing this. Greatest common divisor. The LCM. You know, I don't like copy and pasting code. I don't, but you know, it has its places. It has its places. It has its places. So A, usize. For this type of function, you actually would use comp time because you want it to basically take any type if you want. If B is equal to 0, return A. God, this is such weird indenting. It's going to return a usize. Just a usize? Yeah, no need for that thing. Okay. Okay, and then well, LCM is 1. Yeah, we're just gonna take A and B, do the LCM, and then take C, do the LCM. Let's say var just lengths is equal to path length of 2 and slice, just because it makes it a little bit easier to work with. 2 long slice, so path 2 is equal to the lowest common multiple between length 0, lengths 1, and we're going to go for 2 dot dot lengths dot length n parts 2 is equal to the LCM of the LCM and n. Let's see what you'd say. Key. Where is this? This dot star. Dot star. Starting paths dot items. Expected type E size found. Oh, not the LCM of part 2. Attempted to get null value S. Attempted to use null value. Of where? Starting. That's up there. Why would this break that first bit? Oh yeah, I guess it doesn't really work here. We have to uncomment, we have to comment out the part 1 stuff. I don't love it when puzzles do that, but down to 6. Okay. Okay. Yeah, I mean, that makes sense. Let's go back to this then. And before this, let's actually print S of lengths. And I format S for type E size. Any 2 and 6. Oh, 2 and 6 is not right. 2 and 6 is not right. Why isn't it not right? It is not right because it's not right. That's it. It just isn't. And if it gets into X, it's gonna die. 2, 6 is wrong. So S starting path dot items. Yep, okay, that's all fine. Each time we go around, print current, which is just S. So we go 11A, 11B, and just one more time there at the end. 11A, 11B, 11A left, 11B, and Z. Okay, and then it goes 22A left, 22B, 22B right, 22C, 22C left, 22Z. Alright, dog. Oh, I just had to take a little pause. Right, where were we? Oh, God. I got lost. Yes, so this is wrong. Let's just check the example here. Okay, so UI 11A, 22A. So in this example, you end up entirely on node. Okay, so hold on, I'm confused. Should it be 3? Right, my question is, should it be 3 because that's how long it takes to reach Z? But then you haven't finished your instructions. Okay. Here there are 2 starting nodes because they both end with A. As you follow each left-right instruction, use the instructions to simultaneously navigate away from both nodes you're currently on. Repeat this process until all the nodes you're currently on end with Z. If some of the nodes you're on end with Z, they act like any other node and continue as normal. So I think yes. No, you have to follow each left-right instruction. Use that instruction to simultaneously navigate away. But the thing is, I'm not actually sure because we reach a Z there, and like, would we then stop? Would we kind of halt? I'm not super confused. I'm a little strange. So ends with A, all paths at the same time until they all simultaneously end up at nodes that end with Z. So I think yes, it should be 3. We should kind of continue. And we do length plus, but if we say current and oh wait, yeah, we say if S2 is equal to Z, let's break out the loop. Break out of this for loop. Or do we break out of the while? I'm not actually sure. Let's see what this does. Okay, 2, 3. So we get some numbers and we get the LCM. No. The answer is too low apparently. Yeah, I'm not sure if this is right. I'm really not. Because we end up with Z. That's Z, but do we have to follow all of them? Oh, you know. Okay. This can't be right then. Like, I don't think this last change was correct. I'm gonna cancel it out. I'm gonna remove it, so we end up with this again. Yeah, this is probably the same thing I had for part 1, so this is more right. And this was wrong. Oh, well. 2, 3, 4, 5, 6. Is it possible that I'm off by 1? No, that was fine on the example, so. I think this is too low. I think I've done this one already. Yeah. But is that really the lowest common multiple? Let's double check. LCM calculator. Lowest common multiple. Let's enter these numbers. God, that is a very bright page. Calculate. No. That's quite wrong. So maybe our LCM function is wrong. Yeah, we should always kind of end up with something more sizable. Oh wait, what am I doing? This is length, not. Oh god. Lengths n. Oh, am I just a little bit silly? Oh, let's go. Okay, that didn't take that long. I was just a bit silly to realize that last part, but overall, not that bad. Pretty cool. All right, thank you guys for watching, and I'll see you tomorrow.